I'm from Baltimore, you say you was, I never see you. What part you on? I got some family on the Alameda. I love my city, that's about me, and I bet they know me.
Hi, I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard. Momentum is one of the cornerstones of mechanics, just like energy principle and conservation of energy, for example. And they both originate from Newton's second law. So we'll start from there in this case as well to see what momentum is all about. So Newton's second law says the net force equals mass times acceleration. And again, the acceleration can be written as the time derivative of velocity. But this mass is constant, if it is constant. Most cases it is, so then we can do this. So we can bring the mass inside the derivative. And here we have the product of m times the velocity vector. And that is called the momentum, denoted as p. This is in fact the form that Newton presented his second law instead of the ma. Anyway, we learned from this that the momentum is product of the mass times velocity. So an object with large speed or heavy mass has large momentum. But we're not done with this one yet, so let's separate the dt or the d variables on the different sides and we'll integrate from there. So we bring the dt on the left hand side and we have only dp on the other side. And integration limits are as follows. So here we go from t1 to t2 because we're integrating over time. We're integrating the force F over time. And on the right hand side we just integrate the momentum. So we go from p1 to some p2. And we leave the left side as it is for now. And integrating this one on the right hand side just gives p2 minus p1. So the change in the momentum equals this quantity here, the time integral of force. And this is called impulse, J. It is in the same direction as the force, so it's a vector quantity, as I noted here as well. Here's one way how we can evaluate this integral. So if we plot the force F as a function of t, then the integral is just the area under the red curve in this case. If we are in a lucky position that the force is constant, so then the F comes out of the integral. In that case, the J would just be F times the elapsed time, like this. And that corresponds to the case of the green box where we see that the force is constant. So the impulse is just the force multiplied by the time t2 minus t1. Also, what is shown in this figure is that the area on the red curve is in fact the same as under the green one. So we can calculate the same change in momentum, the same impulse, by having an average force in such a way that the areas between these two curves are the same. Anyway, so this is these two are the vector forms of the momentum and impulse relation. A lot of times, however, we calculate them by the components, so we can separate the impulse in x and y direction in the two-dimensional case. So in x direction, we can say that Jx is momentum in the final position minus initial position in the x direction, and momentum in general is m times v. Like this. And then we can separately analyze what is happening in the y direction, so we have momentum in y direction in that case. It's p1, so mass times velocity in the y direction in the final position minus initial position. So from this case, I think it's clear that if we can evaluate the impulse, then we can tell something about the final velocity if we know the initial velocity. And that is the power of the concept of momentum and impulse when they work together. Let's forget the complex-looking integral formulas for a while and consider the following. We are saying that the change in momentum p2 minus p1 is same as force time the elapsed time, so like this. So let's imagine this is like a simple one-directional motion, force is constant. So we can formulate the law of momentum and impulse like this. Then if you remember what is the change in kinetic energy of an object when a force is acting on it, then it's force times the changing distance. So these two are closely related, and oftentimes they are both needed to solve mechanics problems. And just to illustrate the difference between momentum and kinetic energy, let's consider the following example. Here is a ball that flies at the velocity v and has mass m, and we need to stop it with our hand. And we have two balls. So one of them has mass, okay, let's call this ball 1, and we have ball 2. So the first one is 0.5 kilograms. The other one is lighter, only a fifth of that, 0.1 kg. The heavier ball is flying at 4 meters per second. The lighter one much faster, 20 meters per second, 5 times faster. So this means that the product P, which is mv, that's going to be same for the both. So 2 kg meters per second, and also 20 times 0.1 is 2 kg meters per second. And the question is, which one is hard to stop? If you think about the terms of a momentum, so we need to apply this impulse, J. It's the same for both. So if we are able to apply a force F constantly by our hand, it takes the same amount of time to stop them. But now we also have to consider how much work do we need to do to stop it. So this is the work, F times delta S. And that is same as the initial kinetic energy. So kinetic energy, which is half times mv squared, that's going to be 4 joules for the lighter ball and 20 joules for the lighter ball. And this difference comes from the fact that the velocity of the kinetic energy increased at the square of the velocity, where momentum only was a function of v itself. So in order to stop the second ball, the lighter ball, we need to do 5 times more work. And again, if we would have to apply, or we are able to apply only the certain amount of force, our arm would swing back 5 times more because of the delta S term here. So your arm would take a much bigger strain while trying to catch the ball. So that's one way to think the difference of momentum and kinetic energy. The other one is changed by impulse, and the other one by amount of work. Here's another example. A race between 2 ice gliders. They complete the same course with the length of delta S, and there's a constant force F blowing on the sails. The question is, which one has the greater momentum? So we're looking for momentum for the both vehicles. Let's make a similar table as we did before. So we have boat 1 and boat 2. The mass of the first boat is m. For the second one it's 2m, as we see from the figure, so it's twice as heavy. Velocity. What can we tell about velocity? Well, all we can say for now is that, let's say the other one, the boat 1, has velocity v when it crosses the finish line. So we need a little bit help here, because without v we cannot calculate momentum, which is m times v. What about the kinetic energy? As stated here, change in kinetic energy is force times the distance. And because they both are under influence of the same force for the same distance, their kinetic energies must be the same. So let's call this just k, so it must be k for the other one as well. And from here we can say, so kinetic 1 is same as kinetic 2. So kinetic energy of the first one is half times m v1. Let's call this v1 like this. So, and that's half times the mass of the other one is 2m, and its velocity is some v2. So halves and m's cancel, and we get that v2 is square root of v1 squared divided by 2. So v1 divided by square root of 2. So it's a little bit slower. And now let's calculate the magnitude of the momentum. So that's going to be m times v1, and the other one is going to be 2m times v1 divided by square root of 2. So 2 times for square root of 2 m v1, and that is same as square root of 2 of m v1. So as we see, the boat 2 has a greater momentum, and we needed the conservation of energy to solve the problem for momentum. And this is very typical for mechanics problem. You have to resort to both energy and momentum principles, and sometimes throw in the impulse if you know how long the force acts, or we might need to use the work if we know what is the distance that the force acts over.
Club bass.